Welcome back to the series on graph theory. In today's video, we'll be talking about a special type of graph called a tree. So let's start out by defining what we mean. So we sort of do a top-down definition and first say that an acyclic graph is called a forest. And just to be specific, an acyclic graph is a graph that does not have any cycles. Now, second, we call a connected forest a tree. As an example, let's consider the following graph. This orange graph is acyclic, so it's by definition a forest. However, it contains two connected components, so the whole graph is not connected, and so this whole orange graph would not be a tree. However, if we restrict our attention to either one of the connected components, for example, the one here on the left, this connected component, considered as a graph for itself, would be a tree. And so would the connected component on the right be. So either of these two graphs considered separately would be trees, but the orange graph considered as a whole would be a forest. Thus, the terminology is kind of fun because a forest consists of trees. Next, let's introduce some terminology for talking about parts of a tree, so we could call this tree anatomy. Let's draw a nice example of a tree. Okay, so for a given tree, then we call the vertices of degree 1 its leaves. So that would be the vertices that I'm now circling in green. So the green vertices are called the leaves of the tree, and the rest of the vertices are called the tree's internal vertices. So that's these vertices I'm now circling in red. These are called internal. We can now think about removing parts of the tree, so we could cut off one of its leaves, and this is sometimes called pruning. If you're not a native English speaker, then you might not know this word, but it's the word that one uses for, well, cutting off parts of trees. For example, if you have a tree in the garden, every year you need to cut off some of its branches, and that process is called pruning. And now we use the same word in the context of graphs to describe cutting off parts of trees. We now make the observation that if we remove a leaf from a tree, then what we get as a resulting graph is again a tree. So this is a small lemma. Removing a leaf from a tree yields a tree. Let's think about why this is true. Well, we know that a tree is by definition a graph that is both acyclic and connected. And now we can think about whether removing a leaf from a graph that's acyclic and connected can change either of those properties. Let's first think about cycles. So if we have an acyclic graph, can removing some vertex of that graph introduce a cycle? Well, I think it's pretty clear that this cannot be the case, because in order to introduce a cycle, we'd have to add some additional edge. So if we remove a vertex, we're definitely not adding an edge. Hence, if we have an acyclic graph and we remove any vertex from that graph, the resulting graph will still be acyclic. Therefore, we know that if we have a tree, then if we remove one of its leaves, the resulting graph will still be acyclic. Now, what about connectivity? So the question is whether we can disconnect a tree by removing one of its leaves. And remember, the leaves are by definition the vertices of degree 1. Now suppose we have some tree, which I'll just draw as a blob because we don't know exactly what's going on, and we'll call this tree T. And suppose that we've removed some leaf from T and we've managed to obtain a graph which is no longer connected. In particular, we'd have, two connected components, and one of them would contain a vertex V, and another would contain a vertex W, and in the graph T without one of its leaves, these vertices would be disconnected from one another. So maybe I'll draw these two connected components that are now part of, so this would be, say, a component C prime and a component C, and these are part of the graph T minus some leaf L. Now we know that in the original graph T, it's a tree, so it's connected. We know that there has to be a path between the vertices V and W, just by the definition of being connected. So I'll draw this path in green, and this is a path in T. However, in the graph T minus L, so that's the tree without one of the leaves, this path no longer exists. So how is this possible? Well, the only way that this is possible is that we've removed one of the vertices that is part of this path. So that, in fact, this would actually be the vertex L. But now L is a vertex that is internal to this path from V to W, and so that means that L has degree at least 2. Otherwise, it would not be possible for L to be part of a path. So, in fact, we supposed that L was a leaf, so that it had degree 1, and now we find that L has degree 2. So this is a contradiction, and that means that this situation can't occur. So in fact, removing a leaf from a connected graph has to leave the graph connected. In summary, we've seen that we can't introduce a cycle by removing a vertex from an acyclic graph, and we've seen that if we have a connected graph and remove a vertex of degree 1, so in particular if we remove a leaf, then the resulting graph is still connected. So if we have a tree, which is both acyclic and connected, and we remove a leaf, then after the result is still acyclic and connected, and so that proves this lemma. This lemma will be really useful when we do proofs by induction, because if we have some tree, then we can just remove a leaf and we get a tree that has order strictly smaller than the original tree. And this will be a standard move for doing induction proofs with trees. Another useful fact is that every non-trivial tree has at least one leaf. In this setting, non-trivial just means that the graph has at least one vertex. Why is this the case? Well, let's consider some non-trivial tree T, so that means it has at least one vertex, and now we look at a maximum path M. By maximum path, I mean the path of longest length, and this has to exist because T is finite. Now in the case where T only has one vertex, this maximum path would be the trivial path, which just goes from the vertex to itself, so has length 0. However, if T has at least 2 vertices, then T has to contain an edge because it's connected, and so the maximum path will have length at least 1. In any case, I claim that the end of this path has degree 1. Why should this be the case? Well, suppose, for the sake of contradiction, that this vertex has degree strictly greater than 1. This means that aside from the neighbor that is directly next to it on the path, it has at least one additional neighbor. Now suppose for the moment that this neighbor is not part of the path M. In that case, we could extend M by just adding this additional yellow edge to the path, and we would get a strictly longer path, which is a contradiction because M is already the maximum path. So it's not possible that this yellow vertex here, which is the additional neighbor of the end of the path, it's not possible that this should not lie on the path. Therefore, in fact, this additional neighbor has to be part of the path M already, and it's a neighbor of the endpoint. And now we see that we get a contradiction to the fact that T is acyclic. Because if we look now, we can just go from this vertex along the path M, and then we have closed the cycle with the additional edge that we've postulated. So here we would get a cycle. But this is not possible because T is a tree and therefore acyclic. Therefore, if this endpoint has an additional neighbor, that means it has degree at least 2, then in any case we get a contradiction, because that neighbor can't lie outside of the path M, and if it lies on M, then we get a cycle, which is also a contradiction. Hence we can conclude that this endpoint doesn't have any additional neighbors, and so is of degree 1. This shows the claim that this endpoint is of degree 1, and so in particular, our tree T has a vertex of degree 1, which is by definition a leaf. And so we've shown that every non-trivial tree has at least one leaf. Now it's possible to get a stronger statement by observing that this path also has a second endpoint, which by the same argument as we used for the other endpoint, again has to have degree 1. So this is also a leaf. That means that if the two ends of this path are distinct, then our graph T in fact has 2 leaves, namely the 2 endpoints of the path M. We can now ask when it's the case that these 2 endpoints would be distinct, and we see that this would be the case if our tree T has at least one edge. In that case, we have a path of length 1 at least, so the maximum path has to have length at least 1, and so the endpoints would become distinct at that point. In fact, if T has at least 2 vertices, then it has to have an edge because it needs to be connected, and so once our tree has at least 2 vertices, it has 2 distinct endpoints for the path and therefore has at least 2 leaves. So there's really only one case where we have an exception, namely when T consists of a single vertex. In that case, the maximum path M is just a trivial path and the 2 endpoints of M coincide, and so the tree with just one vertex obviously just has one leaf, but that's really the only exception. As soon as our tree has more than 2 vertices, we get 2 leaves in our tree, at least. In any case, the statement that we've proved that the tree has at least one leaf is generally sufficient for doing induction proofs, because we can say that, we have some tree, and it has at least one leaf, and now we can remove it, and the resulting graph, which is strictly smaller in size, is still a tree, and that gives us a basis for induction. All right, this concludes the definition and some of the most basic properties of trees, and next time we'll be looking at how we can characterize trees using properties that we didn't include in the definition. So we'll basically see 4 different ways of thinking about trees.